Okay, so let's start 4.1. So direct proof of counterexample introduction. This is where we start actually proving things, but we're going to start really slow. And we have two methods of proving a theorem or a statement, right? Either if it's true, we need to directly prove it. If it is false, then all you have to do is find a counterexample, which we'll talk about later a lot more. But right now, the assumption that this book makes when it comes to proofs is that this book assumes you have knowledge of algebra. So just the basic, like all the laws of algebra are assumed. Next thing is we understand that the property of equality for all objects A, B, and C, the following are true. So that you understand that if A is equal to A, that these are completely equal. We also know that if A is equal to B, that means B is equal to A. Number three, if A is equal to B and B is equal to C, then A is equal to C. So this is transitivity, right? And we use the principle of substitution. So we assume that you understand substitution. So for all objects A and B, if A is equal to B, then we may substitute B wherever we have an A, right? And we've done that. I'm sure you've done this back in basic algebra, doing substitution or plugging in a number, that kind of stuff. We also assume that there is no integer between 0 and 1. So if you have an interval from 0 to 1, these are the only integers, right? The next integer would be 2. And the set of all integers is closed under addition, subtraction, and multiplication. So this means that the sums, differences, and products of integers are still integers. So for example, if you have 2 plus 2, you get a 4, right? 4 is still integer. 2 and 2 are integer. No matter what combination of numbers that I choose, 5 plus 7, 5 minus 2, I'm always going to get an integer with addition, subtraction, and multiplication. Okay. So that is pretty clear, I think, what closed means. Closed meaning that there's no way I'm going to get a different type of number, right? There's no way I'll get a fraction or a square root. It's always going to be integer. Now let's talk about definitions of even and odd. So an integer n is even if and only if n equals twice some integer. So if you can write a number as 2 times something, it's considered to be even. An integer n is odd if and only if n equals twice some number plus 1. So symbolically, the easiest way to write it is n is even if you can write it as 2 times something. N is odd if you can write it as 2 times something plus 1. For example, the number 2 is even, right? 2 times 1 is even, so that fits this definition. The number 3 would be 2 times 1 plus 1, so that fits this definition. So that's the definition of even and odd. So let's do some examples. So here is the first question, example 4.1.4. So we're going to use the definition of even and odd that we just wrote down to prove the following. Okay, so part A, is the number 0 even? Well, the definition says that if you can write it as 2 times some number, then it's even, right? So the answer would be yes, because I can use the definition. Because 2 times 0 is equal to 0. So 0 is even, right? Part B is negative 301 odd. Okay, well, if we ignore the negative, let's not even deal with it. So the answer is yes, but let's show the justification. So pull out the negative, don't even worry about it. I'm gonna work inside here. So if I break off a 1, right, that you agree that this is the same as negative 301. So this would be the same as saying negative times 2 times 150 plus 1. So I can write it as 2 times some integer plus 1. So that means yes. That's why it fits the definition, odd. C. If a and b are integers, is 6a squared b even? So the answer is yes, but let's show our justification. So 6a squared times b is equal to, you agree that I can pull out a 2, right? Giving us a 3a squared b. Now, this doesn't matter what a and b is now, right? Let's pretend that this turns out to be an even number. 2 times an even number is still even. This turns out to be odd. 2 times odd is still even. So since I can write this as 2 times an integer, going back to the definition, then yes, it is even. So because we can rewrite this as 2 times some integer d. All right, let's go to the next one. Is if a plus b are integers, is 10a plus 8b plus 1 odd? Well, yeah, I think it is. So yes, because, let me show you, because you can write it as an odd. So if you factor 2 only from the first 2 terms, you end up with 5a plus 4b plus 1. So you have 2 times a number plus 1. 2 times an integer plus 1. Remember, that's the definition, right? We'll look at them in case you don't remember. 2 times some integer plus 1. 2 times, that would be odd. 2 times any integer is even. So some integer, I don't care what it is, times 2 plus 1. So by definition, right? In other words, same thing here. 2 times an integer, that's by definition as well. All right, so that's first example. Let's do another one. Okay, so before we do another example, there's always another definition, right? As you can see, this class is about understanding definitions in order to do the problems. And as we get to proofs, that becomes more and more important. Okay, so an integer n is prime if and only if n is greater than 1, and for all positive integers r and s, if n is equal to rs, then either r or s is equal to n. So that's a requirement for prime. Okay, an integer n is composite, meaning you can factor it into more than one part. So it's composite if and only if n is greater than 1, and you can write n as r times s for some integer r and s, with r being between 1 and n, and s being between 1 and n. Okay, so let's do an example. Let's see here. Let me pick one. Okay. So 4.1.2, prime and composite. Is 1 prime? Well, look at the definition. It says to be prime, and an integer n is prime if and only if n is greater than 1. So right away, no, by definition, n must be greater than 1. B is just basically find the numbers, the first 6 prime numbers. So 2, 3, let's see, anything that's not divisible or can be written that way, right? For all positive numbers R and S. So if N is equal to RS, then R has equal to 1. So an easy way to think about this, if prime is confusing in this definition, is that the prime number can only be written as itself times 1. For example, factoring the number 2 can only be written as 2 times 1. 3 is 3 times 1. 5 is 5 times 1. 7, 11, 1, 2, 3, 4, 5, 13. So all these numbers can only be factored by the number 1. Nothing else divides into them except 1 and itself. That is what that definition is saying. Composite is basically anything that can be factored. So the first one would be 4, 6, 8, 9, right? These are 3 times 3, 2 times 2 times 2, a bunch of factors here. 12, like 10 actually, 12. 1, 2, 3, 4, 5, 6. Did I forget any? No. 4, 6, 8, 9. No, that should be it. So no big deal, right? So this fits the definition, and I can write them as some number times something other than itself. Okay, let's do another example. All right, so let's talk about proving existential statements. So there existed X and D such that Q of X. So any general statement like this, this is only true if and only if Q of X is true for at least one X and D. So you're just going to find one element X in that set D. So let's do this example here, constructive proof of existence. So there exists an even integer, n, that can be written in 2 ways as a sum of 2 prime numbers. Okay, so prove that that is true. There exists an integer n that can be, so I just need to find 1, right? So in the book they use a couple of examples, but let's use this one here. So you know what? Let's let n equal a basic number like 10. Then 10 is equal to 5 plus 5, which is equal to 3 plus 7, right? And 3, 5, and 7 are all prime numbers. So the sum of, there exists an even integer that can be written in 2 ways as a sum of 2 prime numbers. So here are 2 different ways. No big deal, right? Part B, suppose that R and S are integers. Prove there exists an integer k such that 22r plus 18s is equal to 2k. So we gotta think of a number. It can be written this way. Like, well, let's say let k equal 11r plus 9s, right? So you agree that technically 2k would be equal to 2 times 11r plus 9s, right? Okay. One more. Okay, so we know that this is just a sum of integers. So k is just 11 times integer plus 9 times integer. And we said that addition or integers are closed under addition and multiplication. So if we substitute that into 2k, we can show that that is still an integer. So yeah, we can write integer in this form. So we show that there exists a k that is an integer written as 2k. So nothing crazy. All right, so now let's go over disproving by counterexample. So to disprove a statement of the form, I wrote that twice. For all x, if p of x then q of x, all you have to do is find a value of x in D for which the hypothesis p is true and the conclusion q is false. So p needs to be true and q needs to be false. You find an x that does this, make one specific example, and you disprove the entire thing. So for all real numbers, a and b, if this, then this. So if the squares are equal for all real numbers, are the originals equal? Well, no, that's not true, right? For example, easy one would be, let's see here, counterexample. Let's see if we use the negative numbers here. So -1 squared is equal to -1 squared, right? Let's say, sorry, be different. Yeah, this will work. So -1 and 1 are both equal to 1, right? So these are equal, even though they're different. But -1 is not equal to 1. So this is an example. This is a counterexample. So formally written, you'd say counterexample. Let a equal 1 and b equal -1, then a squared equals 1 and b squared equals 1. So a squared equals b squared, but a does not equal b. So this is a contradiction. Kind of a counterexample here. So that's how you show that this is false. Okay. So we'll do some more examples on next, on part 2 of this video. So we'll stop here for this part.